Good morning, good afternoon, good evening, everyone, from wherever you are watching us from. Welcome. And today we are together here with you after so many lectures, after so many distinguished events, panels. Here comes the last academic event of the SSP22 online academic program. My name is Göktuğ Karacaloğlu. I'm the program director of the SSP, and it's my great pleasure today to be the master of ceremonies of this prestigious event and address you from our SSP online operations studio, which is indeed located in the IST Tagus Park campus, Oeiras, Portugal. As many of you hopefully followed, we have kicked off this program 6 weeks ago, where our 15 participants representing 9 nationalities were tasked to work on a single team project, which required them to explore new methodologies in search for life. It is always a challenge, but also an amazing learning opportunity to work with diverse and international teams, where you have language barriers, different cultural norms, and people with different levels of experience. As part of such a team, it is your responsibility to hear each other's voice individually and learn together. But in an online program, indeed, the challenge is much greater than that, since the participants are only virtually connected to the rest of the team. And if that's not enough, they are also operating on different time zones. So some of them indeed being 15 hours different from the others. That is, for the last 6 weeks, ladies and gentlemen, some of our participants have been starting their days as early as 1 a.m. local time, pretty much in the middle of the night. So kudos, everyone. In such a challenging context, here at the SSP Online Program Studio, we have tried our best to support them with many supplementary activities, including daily seminars, interactive workshops, and project-specific activities. Today, on their last day of SSP22, we will be tuning in and listening to our participants as they walk us through a summary of their findings, analysis, and recommendations. Maybe a quick note here on what to actually expect. As part of the SSP curriculum, we many times emphasize the importance of storytelling and public outreach and to get your message across to your audience. In that regard, we have also asked our participants to demonstrate this learning as part of their final team project presentation. That is why what we will watch today will not be a half an hour PowerPoint presentation, but rather a more interactive session where our teams will use the power of media technology available to them. I would like to take also this opportunity to acknowledge and thank the chair of this team project, Dr. Jacob Cohen, and the associate chair of this project, Ms. Alice Ryan, who have done a tremendous job to lead the project. And also the project assistant, Thomas Chrétien, and all the other teaching associates and experts who have made incredibly valuable contributions to the project work. Thank you. So, on my screen, indeed, I can already see the presentation team, as well as the project chairs, excitedly waiting for me to pass the floor on to them, which I will do in a minute. But first, let me extend my thanks and appreciation to our distinguished guests and experts, jury members who are with us at the moment following this presentation. Some of them virtually, some of them here in Oeiras, Portugal, in the auditorium, and shortly we'll be challenging our participants with their comments and questions. With that, ladies and gentlemen, I would like to now pass the floor to our esteemed chairs. Dr. Cohen, Ms. Ryan will walk us through their 6-week journey. Jacob, Alex, the floor is yours.
Thank you, G2. I really appreciate all the work that you do and your team to make this happen. And so It is both a happy moment and a sad moment that we're here at the final presentation of our TP, New Methodologies for the Search for Life, or as we, the Associate Chair Alex, the Teaching Assistant Thomas, and I refer to it as It's Alive TP. And obviously this comes from a movie, and it may be copyrighted, but you can go on YouTube and see it. Every time I undertake chairing a TP, I'm amazed at what could be achieved by a group of participants from different backgrounds, cultures, nationalities, etc. You could add all the differences that make humanity singularly beautiful. At this time, being a virtual TP, working at different time zones and various internet capabilities, as you saw, is really both a challenge for us, the chairs, and also the participants. But we're able to work with it and create the TP experience as previously done. So I'm also saddened by what could have been achieved, would we have had, and I know I also speak to the participants, another day, a week, month, or year. This in part is what ISU is all about. It is about putting all the spice of humanity in a pressure cooker for a few weeks to develop novel ideas that challenge how we see or interpret a topic and create lifelong friendships. This TP consisted of 15 participants representing 10 nationalities. They tackled the question of the search for life and focused on a mission to Enceladus, a moon of Saturn. As they worked on the search for life, they demonstrated life. I would like to thank all the participants, the TP leadership partners, the SSP staff, the global reviewers, and ISU as a whole. ISU's mission is a noble and great mission, and I hope it catches everywhere across the globe and beyond. And now I will turn it over to Alex, who also has a few words to say. So thank you very much again, and thank you to the participants for this great, great opportunity to work with you.
Thank you so much, Jacob. It's been a wonderful time to work with you. And every single time I get the chance, I always learn something new. So at the start of this program, there was 15 strangers, but now I'm very confident in saying there are 15 very good friends among this call. The participants have worked really hard, and myself, Jacob, Thomas, and on behalf of the entire ISU team, we're exceptionally proud of what they have been able to do, given all of those extra challenges, extra time constraints, extra difficulties around the virtual format. I won't take much of your time. I just wanted to say thank you very much to all the participants for being so welcoming and so wonderful. It was an honor to get to know all of you, and I cannot wait to see what you go, where you go, and who you go with in the future. I won't delay any further. I want to see what these guys have put together. Thank you.
The year is 2100. The Earth is an incredible place. Poverty and war are a thing of the past. The Earth enjoys unlimited carbon-free energy. The oceans are abundant and clean. The climate is stable and perfect. Global cooperation and trust are at all-time highs, and space is an open and incredible place that the global population regularly visit. One event in human history triggered sovereign nations to come together under one umbrella. A mission that was planned in 2022 by a team of space dreamers and executed in 2030. A mission that changed the way the world looked at what life really is. An event that made the world realize that we are one species. An event that made us understand what it means to exist. This event was called Sentient.
Come on, everyone. In you come. In you come. Guys, we're going to have all day. Come on, in you come. Guys, welcome. And thank you all so much for being here for Sentient Day. I am incredibly excited. I'm sure you are all super excited as well. The fact we're actually going to have Alina in this room to speak to us is incredibly exciting. But before we get to that point, I thought it might make sense for us to recap that incredible mission via this documentary, if we can just get it to work. So let's have a crack.
Firstly, let us ask ourselves, what is life? Different attempts at defining life have been made by humans. As part of our research, we have strived to create a whole new comprehensive definition. We, at the Sentient Project, define life as a process that takes place in highly organized organic structures, characterized by being pre-programmed, interactive, adaptive, and evolutionary. These structures are governed by chemical activity that involves water, organic molecules, and habitable environment conditions, since these conditions are requisites for life as we know on Earth. There can be life in conditions that are different from the ones that we know. Now that we have identified what we are searching for, it's also necessary to ask ourselves, why? Why should we search for life in other worlds? Whether life exists beyond Earth is one of the greatest questions of all time. Different religions and philosophies have endeavored to answer this question, although no definite answer really exists. Having an answer to this question, are we unique in the universe, would change our view of this universe forever, even if it ends up being a universe in which we cannot find any other life form. This curiosity has captured people's imagination, leading them to seek new adventures beyond our planet Earth. Inspired by childhood authors, space and science fiction magazines featuring new planets, spaceships, and alien life, enthusiastic astronomers and novelists, artists, astrobiology scientists, and astrophysicists, they all, well, mostly, welcome the uncertainty of what lies ahead in space exploration. Are we alone in the universe? So, what exactly are we looking for which will detect life on Enceladus? Biomarkers are the signatures of life left behind by cellular processes. The Cassini mission had identified the presence of molecular nitrogen, carbon dioxide, methane, and other compounds, along with water, which are the most basic prerequisite molecules for life as we know it. For our mission, we aim to go a step further and in the plumes and on the surface search for ATP or adenosine triphosphate, which is present in every living organism on Earth and are responsible for carrying energy. We will also measure the percentage of carbon-12, methane, and C6 sugars. This will give us more insight on whether life is or was present on Enceladus. However, we have to be cautious of false positives as well, which are abiotic sources which mimic biosignatures. One way to rule them out is through repeated testing, as well as conducting an iterated search with analog sites. For example, the ultraviolet degradation of methane or carbon dioxide could be a false positive for the formation of carbon-12.
While it's not Saturn's biggest moon, as that distinction belongs to Titan, or even its closest satellite, Enceladus makes a strong case for being one of its host planet's most captivating worlds. Enceladus is a small icy body with massive fissures called tiger stripes. Its surface temperature is minus 201 degrees Celsius. Covering the entire surface of this ocean is a layer of ice 20 kilometers thick. The Cassini spacecraft exploring the Saturnian system found evidence of a vast subsurface ocean encompassing this frozen moon, likely with hydrothermal activity on the seafloor. This ocean underlying the ice dwarfs the waterways of Earth. While oceans on our homeworld cover 75% of the planet to an average depth of just 3.6 kilometers, the ocean on Enceladus covers the entire moon with a layer of water averaging 30 kilometers deep. Geysers erupting from the south pole of that world reveal an active geology at the alien seafloor. Frozen debris from these eruptions spew into space, trailing behind the moon as it orbits its planetary parent, forming the E-ring encircling Saturn. Enceladus' atmosphere is mostly water vapor, small amounts of nitrogen, carbon dioxide, and methane. Enceladus' average distance from the Sun is about 9.5 astronomical units.
Hey guys, Mauro speaking. The first ever Portuguese astronaut now working at NASA. And welcome to the most daunting part of the TP, the engineering and the execution of the mission. Our mission is called Sentient. We have a launch date for 12 August of 2027. We have chosen, of course, SpaceX for the launch, due to its cheaper launching facilities, and this is crucial for such an high-profile mission. In order to save fuel or propulsion power and arrive to Enceladus with a proper delta V, the spacecraft will have a flyby from Earth to Venus, Venus to Earth, and then Saturn for arriving to Enceladus. So all of this was possible due to the Lambert's problem, Human's transfer law, Newton's equation, two-body problem, and all kind of stuff that I will love to teach you, but it's not the time. Moving toward the spacecraft design, the probe is divided into an orbiter that will stay in orbit around Saturn's moon, Enceladus, and a lander, which will have a touchdown on the ice terrain of the moon. Then, the orbiter, of course, is equipped with remote sensing technology to analyze the atmosphere and surface of Enceladus. Then, we will add an instrument called a LIDAR, will help us determine the optimum landing site near the tiger stripes of the southern polar region. So the main goal for the lander is to arrive on the tiger stripes of the southern polar region on Enceladus. Post the impact, the lander will be able to collect samples from the surrounding ice using the instruments on board. It also has its own set of instruments that will work to analyze the surface and subsurface environment of Enceladus from the terrain. Now I will leave you to my other colleague at the engineering team to explain more about comms and all the stuff. For me, it was a pleasure to be here, and now I will need to go back to work. See you guys.
Hello everyone, this is Akshata. I just wrapped up some work. As you can see, I'm at NASA JPL and out on a break. But yeah, let's go talk about the communication system of this mission. Here's how Sentient will talk to Earth and its own little lander on the icy terrain of the Moon. The communication subsystem is equipped with X-band RF link for direct-to-Earth communication from the orbiter. Next, the lander transmits a near-infrared laser beam towards the orbiter's antenna to transmit high amounts of science data at faster rates to be relayed back to Earth via the orbiter. The orbiter to lander downlink is an X-band RF link, which is the radio frequency link. This hybrid communication system, mission to Enceladus HCSME, will feature a hybrid communication system comprising of telantenna, which is a telescope, and an outer layer of RF antenna combined. This system utilizes best of both worlds, that is the RF and laser, to meet the mission objectives. The sole purpose of this hybrid nature is to enhance the science objective and provide flexibility to the science community to explore highly sophisticated instruments without the constrictions of substantial amounts of data to be transmitted. The science can relax. The Enceladus Orbiter Lander Proximity Optical Link is a never-before implemented technological advancement which has been proposed using the existing technologies. And this is how we communicate. Thank you.
Wasn't that just amazing? To think that those 15 people managed to come up with this entire mission and plan and execute it so brilliantly. Hard to believe. Now, guys, we must have so many questions. Should we start with online? Online. Any hands up? Anyone from online got a question? No one? No one from online has a question. Oh, okay. Stay on site.
Professor? Yeah, Simon. Wow, this looks like a very ambitious mission indeed when it was formed. But my question is, how did they fund it? Who paid for it, actually?
Remember, this is the year 2100. All the questions asked by students are directed to Siri, an AI bot in the cloud. Siri then searches the web to find the most appropriate person in human history to answer each and every question. Isn't technology amazing?
Great question. You are absolutely right. Despite the profound impact that a positive detection would have on humanity, funding for the search for extraterrestrial life has not been anything close to consistent over the years. As a result of this, the cost has become the main factor that determines if the mission is going to be approved or not. After some extensive research, Sentient decided the best funding model would be private-public partnership, with financing split between government space agencies and private commercial applications. But as you said, this was a really ambitious mission and would be classified as a flagship mission. The team wanted this mission to be an international collaboration, so it budgeted for 70% of the finance to come from a majority public funder with 15% from a minority international partnership, and the remaining 15% from a private and commercial funding means. Although the majority of the financing did come from public funds, the team did come up with some really innovative and new private funding measures, which have since been used many times to fund other missions. Firstly, a space lottery where the prizes include a zero-G plane suborbital flight on Spaceship One or a trip to the International Space Station. Secondly, the team raised funds via selling the rights for a documentary to Netflix. The subsequent documentary was legendary and still gets many views today. Thirdly, the team implemented an NFT or non-fungible token sale for the one-of-a-kind of the photos that the mission delivered. These images still get transacted for huge amounts today, and for every sale, NASA receives 3% of the sale price. The mission eventually ended up costing $5 billion, right in the middle of the range between $4 to $6 billion, which the team predicted.
Yep. You in the back.
Thank you. So finding life must have come with some interesting legal and regulatory challenges, right? I was wondering, how did the team think about that? Thank you.
Very interesting question. Of course, looking for life in space has its shares of legal challenges. The main one being respecting planetary protection, meaning the mission should not contaminate the celestial body with Earth pollutants and vice versa. This question is addressed in Article 9 of Outer Space Treaty of 1967. It covers harmful contamination, which should be interpreted as a biological contamination. Concerning the appropriate measures, the Non-Governmental Scientific Board, COSPAR, published the Planetary Protection Policy, PPP, that gives the specific requirements according to the mission type.
Indeed, concerning our mission Sentient, a program lander were planned. Therefore, requirements of Category 4 had to be observed. As you can see, the mission had to have a bioburden, clean room facilities observed, and all these kind of requirements. One of our concern was that the PPP is not a legally binding document, but this concern was rapidly addressed as NASA implemented these requirements in its own regulation. The same can be said to other space agencies like ESA or JAXA, for instance.
Furthermore, as Article 3 of the OST directs, space law is in compliance with international law. Therefore, environmental law, which is a branch of international law, applies to space and can prove useful. For instance, Article 3 of the Convention on Biological Diversity could apply to both back and forward contamination, increasing the scope of its legal applicability.
One of our main issues was intellectual property. As a possible international cooperation with ESA, European directives had to be taken into consideration. Therefore, we wondered if the discovery of any form of life could be patentable. Thankfully, the issue was rapidly solved, as the question can only be raised for scientific invention and not for scientific discovery.
However, we did have legal challenges, knowing that in 2022, a lot of countries adopted or were in the process of adopting national licensing regimes specific to the new space activities that did not address the COSPAR PPP requirements, which is an issue as a planetary protection and scientific investigation might be not in the private sector's priority, especially if there is a potential financial opportunity deriving from the extraterrestrial microbe.
Nonetheless, COSPAR planetary protection was developed to ensure the scientific integrity of life detection missions. Lacunas were found concerning Enceladus' environment. In 2010 already, the extension for planetary protection from science protection to protection of planetary environments was considered, but nothing changed till 2022. Thankfully, due to the Sentient mission, planetary environmental ethics were added into the planetary protection policy, and the private sector became as concerned about planetary protection as the public agencies.
You with the red hat.
Sir, I have a question, sir. Sir, okay. Thank you, sir. First of all, thank you so much for giving us the lots of the information. And my question is, but why did they choose the Enceladus for the mission? How did they know that would be the best place to find life? Thank you, sir.
Well, that's a great question. Thank you for asking. With the Cassini mission, we discovered plumes of icy water and gas being vented from the Enceladus South Pole. These plumes were laced with grains of silica-rich sand, nitrogen, and organic molecules. This indicated to us possible hydrothermal activity in Enceladus' subsurface ocean, and we believed that hydrothermal vents were powering an entire ecosystem of deep-sea microbes waiting to be discovered. And we must remember, back then, no dedicated space mission had ever been sent to explore Enceladus' world.
Wow! It's Alina! She's really here! Wow! It's Alina!
Wow! This is real. This is really Alina. Here, right next to me. Wow! Woo! 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 Woo!
Thank you all so much for your warm welcome. It is really amazing to be here with you today, on Sentient Day. We are part of a living universe. We now know it. A vortex of non-living substances at one end and energy at the other found a balance to create primordial life. In spite of perpetual change, living organisms preserve their integrity, identity, and individuality, becoming self-preservative and self-sustained. Our imagination reels as we stand out under the stars and try, even faintly, to realize the immensity of the living universe. Before sentient, humanity's destiny beyond Earth was on the verge of a new era. This era unfolded with the discovery of life on Enceladus. As anticipated, there were mixed reactions from the public, emotions, disbelief packed with excitement, and even fear of the unknown. But ultimately, this groundbreaking event brought us together. New laws and policies were developed as humanity came to terms with its place in the universe, and we realized we were stewards of the Milky Way galaxy, a galaxy we share with other life forms. The team I'm profoundly grateful to set out to find new methodologies for the search for life, and I believe, looking back, they found something rather precious than these microorganisms. We are nurtured in such a home, our Earth, animated by such love for our environment, inspired by such love of humanity. This extraordinary discovery enabled humanity to grow, bringing countries together in one tightly interrelated community we are today. Since this successful endeavor, new legal frameworks were developed, new ways of partnerships and funding were created and implemented. New ideas in science and engineering emerged. More discoveries await us, and I hope you enjoyed learning more about our mission and our team and our vision. As a final thought, let's come together as humans and lifelong learners. Let's remember to remain united, and let's remain a peaceful, international, and forward-looking civilization, eager to pursue new ways into space exploration for generations to come. Thank you everyone for all your attention, and to my sentient team for believing in our dreams. Thank you.
a wonderful job, Team Sentient. Great, great, great effort for 6 weeks and such a storyline that you indeed take the topic to another level indeed. I would like to actually acknowledge one important thing I think I didn't actually mention before. This presentation of the team project, obviously, in this time frame of 30 minutes, just puts the thing into an aspect of a storytelling. However, there are much more depth into it, and the team indeed came up with, similar to this presentation, a final report and an executive summary of their project, which will soon, in a few weeks, be uploaded in the library of the International Space University. So if you're interested, I highly encourage you to visit our library website, download these 2 documents, and go much more into depth in this topic. All right, with that, it is time to actually get some questions from our experts and from our audience. I well know that all the participants of the team, the 15 of them, are very excited to receive those questions and address them. So for our board of experts, we have, as I mentioned, some with us in here in the auditorium in Portugal, and some virtually joining. So please, prior to asking your questions, briefly introduce yourselves so that our audience who are also watching us online can get to know you better. So now I would like to pass the floor to Eric, one of our members of the team, to kick off and moderate the Q&A session. Eric, please tell us a little bit more of how we will run the Q&A session, please. And then please welcome the first guest expert on the stage. Over to you.
Good morning, good afternoon, depending on where you are located. Thank you. Firstly, I have to say that we are all very thankful to be part of SU, and we are all very eager to answer all your questions whenever possible. So yeah, we can start. Are the interested parties gonna lift their hands up?
Hello. Hey.
Yeah.
Hi. I'm Ruth McAvinia. I'm the co-chair of the Humanities Department here in the SSP Lisbon. But I work in real life as a video producer at ATG Europe for the European Space Agency. So I noticed at the start that your chair said it would be lovely to have more time. Good morning, Jacob. Hope you're well. If you had one more day to work just on the video, what would you do?
Regarding the video, I would say that the most suitable person to answer would be James, who was the idealizer of the whole presentation.
Hi guys, thank you so much. Yeah, it's a great question. One more day, what would we have done? I can tell you the real challenge was to get real live footage. I had the pleasure of going over to the alumni weekend last weekend, and so I got to spend 2 days with the on-site guys, and that helped a lot to be able to get just a few scenes of the auditorium, etc. But it was a big challenge being able to get real live footage and then cut it back in together. If we had one more day, I feel like we could have maybe done a little bit more with the ending part, and maybe be able to get some more real life images rather than try to digitalize people walking onto the screen via Zoom, etc. But on that note, you know, none of us have ever edited a video before at all, and we had a girl on the team called Aruna who did, I think, quite an amazing job of actually putting it all together, because the technical skills to do something like that are actually quite challenging, and very thankful to her that she was able to put it into any shape at all, because I know I would have struggled with that big time.
Yeah, thank you, James.
Thank you very much, and well done. Quite apart from all the technical skills, what really comes across in the video is that you have a story, and it's great to hear all the elements of the story. So congratulations.
Yes, thank you. Can we please have at least in the order that it comes up to me? So Mrs. Filomena, could you please?
Bonus, and I am a teacher for the Waterloo Region District School Board, whose director is Chiwan Chanaka, whose principal is Jason Steary, and whose science consultant is Hebron Gebra Mariam. And my question comes from a perspective of public outreach, which incidentally, I hope they got it on camera that I was one of the people putting my hands up because I really did believe I was in the year 2030. So my question is, who does Sentient see as their audience for the story that we just saw today? When you were making this, when you were looking for all the pictures that Mr. Westwood was talking about, who did you have in mind as your audience? Thank you.
Yeah, for this question, thank you for the question. I'm gonna direct it to Mrs. Alina.
Thank you for the question. Thank you very much for the question, Mrs. Filomena. When we started the entire concept and presentation, and as well we looked on how we reach with this message, we realized that this finding life is in fact for every person on Earth, as the space, the entire space ecosystem and industry started in mid 20th century. In fact, captured everyone on the Earth, from children to adults, as well our grandparents. It was the dream to pursue going to space, but further on, finding life and seeking to find life on different planetary bodies and finding new organisms is in everyone's interest. And I would like to also add that is in the interest of the new generation to step up towards realizing that we are on the age of finding new discoveries. Maybe our grandparents, our parents now, they will say, we don't need to pursue such things. Come back on Earth and think on society level. But the next generation, we want to inspire with such ideas because there's much more to discover. And on our work today, we always want to inspire children coming. Thank you.
Thank you.
Thank you, Alina. I do want to make a request. Well, whether there are people inside on site wanting to ask questions, I can't actually see their hands up. So if they are, I would ask the on-site TAs to help me out on this, because I can only see, for example, the next one would be Carol Carnett. You can go forward.
Thank you. I'm Carol Carnett. I am the English Languages Support Lead for ISU Summer Programs, and I'm part of the ISU faculty. I have a question about the 2002 report. I think Philomena Bonus was part of that team, called Alone. It was, again, about search for life in a way. And I was wondering if you had looked at that report and if there was anything in that report that influenced your approach to this new, very visionary TP report. Thank you.
Yeah, thank you for your question. Yeah, I personally have to say that I did not check that one. Yeah, but it's certainly something that needs to be brought up. I think due to time constraints, probably we cannot reach every type of literature around, so I'm sorry for that. But I will keep in mind that to read it after. Of course, we're always learning. Yeah. Next one, at least in my list, would be Bernard Foing.
Hello, everybody from the online SSP TP. Yes, so yes, nice cartoons, interesting narrative, also the perspective for the future. Storytelling is fine, but it's not space stories studies, it's also space studies in general. So now I'm going to ask you some engineering questions. Yeah? But I really like also the way you went in depth in showing how we can handle signatures of life, because this was, I think, very educative. So it's already a first step. If people read your report, they will learn about what is life and how to search for life. But if we want to send a mission to do it, we need a bit of engineering. So I was not able to find in your report, or for instance, what is the mass budget of your flagship type of mission, the lander mass, how you design it, and you have a number of instruments, very ambitious, a large number, so many more than a flagship mission. So is it feasible? So what is the instrument also, mass budget, and what is the heritage? And how can you organize yourself to be ready for a launch in 2027?
Yeah, sure. Thank you. Thank you for your question. I must add, I didn't say it before, our lead engineer has gone through an accident. He broke his thumb, and that's been 2 weeks already, but he's in the hospital checking it out.
Oh,
so I'm gonna
for him,
yeah, I'm gonna try to approach your question. And regarding the mass, in a conversation with him, that's his name is Mauro. In a conversation with Mauro, it was we took the decision to have a general estimation of the mass. So he was not able in the short time to figure out, to find a correct exact number for the mass, and we have estimated it to be around the size of the Apollo mission, but that would be a very rough estimation. And the next question was the time. So to 2027, I believe to draw up a project management structure, as in a Gantt, for the whole mission of 5 years, it became a very difficult burden for us to have in this short time. We didn't approach the time span for the mission.
So, I mean, okay, we could discuss. I think that Apollo 11, I think, is not a good reference, but you had the example of this lunar orbiter for around the same Enceladus. So it would be good that you go into some of the technical detail, mass budget for this one. And you say you want to do better because you have a quite comprehensive set of instruments, but eventually you could play on the fact that we have more miniaturized instruments that's from the Apollo 11 time, of course. So really look like any mission studies, you have to have a detailed study of payload, so what they do. So you have identified your payload very well, but then you have to do the next step, which is what are the engineering requirements, so mass, power, budget. And from that, you can determine what size of a lander and orbiter you need. And then you will find something which is, I think, much more realistic. And after you have that, okay, then you can say, who has built this payload and are they ready for 2027? So I think you would add in credibility to go to this systematic step. Yeah,
I definitely agree. Well, more detailed analysis sure would be a next step for the mission concept. Sure. I would like to send it to Julia. She can complement on the instrument's mass system.
Yeah, excellent. So good luck. I think it's yeah, good to follow up also to make it a comprehensive and yes, and fulfill the ambition of your mission. Thank you.
Hello, I'm Julia. I was part of the science group, and we built the instruments together with the engineering group. And for this mission, we had orbiter and lander. So for the orbiter, we chose to have some instruments that were proved to be successful in the Cassini's mission. So for the satellites of Enceladus, so a mass spectrometer to determine the composition of and abundance of the plumose gases. Also, the LIDAR, which is light detection and ranging, which works with remote sensing, actually to see which better place would be to land on Enceladus because of the plumes. Also, we have other instruments, but I think I could like emphasize these ones. And for the lander, I would say that we chose to have the organic composition analyzer, which is a mass spectrometer instrument to identify molecular concentrations in terms of mass, and also SuperChem, and to characterize microscale evidence of life, and light measuring instrumentation, which is a technology studied for looking for concentration of ATP in cells. So, I mean, there are some more instruments, but I could emphasize these ones. Thanks.
Yeah.
Thank you, Julia.
Yeah, you have a nice list of instruments. I see that LIDAR, DHM, NIJA, mass specs, many nice things. But okay, clearly try to put a figure estimated mass on it, and so that you can go to the next step to see how you integrate them. And about lander, take into account it's different to land on an object which is 1% of Earth's gravity than to land on the moon, which is 1/6 gravity. So it's you'll have different demand on your lander, so you can miniaturize things that you could not do for our moon, for instance.
Definitely, yeah. Thank you for your contribution. We do have some questions in person. Please, Françoise Espiero.
Hello, can you hear me?
Yes.
So thanks a lot for this video. Very, very nice, very interesting. I was curious to know if you could clarify the process in which the team chose Enceladus as the target, as the destination. There are several candidates in the solar system of planetary bodies which could harbor potentially life. Mars, of course, and some moons of Jupiter or Saturn. So can you please explain why your choice was on Enceladus? Thank you.
Yeah, sure. The most suitable person to answer this would be Julia. So please.
Yes, thanks for the question. As I was saying, the science group actually did a research on target locations, which locations would be better to find life. We decided to do the scope in the solar system at first for terms of feasibility. So after deciding for solar system, we decided we started to make a table of characteristics of the possible places to find life. And based on past studies, first we decided to stabilize which is going to be our definition for life before we look for it. So first, for beginning with our definition of life, which would include organic matters and chemical activity, and also a process that would basically involve water as an ingredient for life, we decided to go for locations that had these ingredients. And based on that, we had on a basis Enceladus, Europa, Titan, Mars, and Venus as possible locations. We decided to go for, we saw that Mars, we already have a lot of research on that, and as we're going for something new, we decided to go to the moons of Saturn at first. We had some drawbacks because they are too new, but we decided to go for it since they have a huge quantity of water in the form of ice. That's why they're called ocean worlds. They have alkaline vents on Europa and Enceladus, and especially Enceladus has tectonic activity. Also, the very much the abundance of plumes on it indicates the presence of hydrothermal activity under the ice. And also that the material from the plumes of Enceladus found in the Cassini's mission indicate that the material is similar to what is found on Earth. So these are the mainly points that we saw that we should go for Enceladus. Thanks.
Thank you, Julia. Still from on-site, we have Suyin.
Hello, SSP. Congratulations, online participants, for completing your team project. I'm Suyin Tan. I am the co-chair of Space Applications Department here on site, Space Apps, and I'm also at the University of Waterloo in Canada. So I just want to again congratulate you on coming a long way. I just quickly previewed the executive summary and the final report, and it looks like you've made a lot of modifications in a very short time frame and also in a fully online environment. So congratulations on a superb collective effort once again. I have a really fundamental question for your TP. Your title of your team project is New Methodologies in the Search for Life. And I agree that this is a new mission design concept for a spacecraft orbiting Enceladus that doesn't currently exist. But I'm wondering, in terms of methodologies, what novel technologies are going to be used and what new findings do you hope to discover? What's the main contribution significance in terms of new methodologies of your TP and proposed mission? And can you just summarize what's really novel that we should expect out of this project? Thank you.
Yeah, sure. We'll give that answer in two parts. So please, Akshata, you can begin.
So for the communication part, we have chosen laser communications, which will enhance the science objective. It has been designed as a hybrid system, which will be like a radio frequency link between the orbiter and the Earth, and there will be a hybrid system for the orbiter and lander link. This will enable the reductions in size, weight, and power on the lander, which will actually enhance the science objectives by increasing the data rates, and the transmission of large amounts of data will be feasible. Now the science community can relax without the constrictions of large amounts of data to handle, and actually add in more instruments that are more crucial to this.
Thanks, Akshata. For the second part of the answer, can we have a Priyanka?
Hello. So firstly, thanks a lot for the question. So in the last 5 weeks of the SSP, we had a lot of time to brainstorm on different ideas and see what all were existing, what all have been done for different missions in the past. Of course, it was not enough time for complete detailed analysis along with the courses, but we did think of things not just in the science part, but also from humanities, from business. For example, we're going to talk about something like generating revenue by selling NFTs from a space mission. We also have in the humanities side something called the future wheel, which was introduced to us in one of the workshops. So we also dabbled a bit into that to see how we could use that for, to project us into the future. And of course, on the science part, we have been looking at something called ATP, adenosine triphosphate, to study the plumes of Enceladus and see if we can detect that. So I don't think that has, so we didn't find research that said that had already been done. So this is what we propose as new methodologies. Thanks.
Yeah. Okay. Yeah. Thank you for the responses. Could you please have Maurizio Nati online?
Hi, good afternoon, everybody there. I am Maurizio Nati. I have some over 30 years of experience in ESA. I am retired now since a while. Some almost around 40 decades of space activities and some experience with ISU. I've been cooperating with ISU, for instance, as chair of the engineering department in the SSP 2019. I have honestly 3 questions, very short, very punctual. First of all, I would like to congratulate for the excellent presentation and the excellent quality of the executive summary and the final report. First point is the mission profile. I would like to elaborate a bit along the line of what one of the predecessor already mentioned about engineering. The mission profile is not evident, is not contained in the final report. I understand the key person, unfortunately, is in the hospital. I'm very sorry for this person and for this situation. Nevertheless, the final, not the draft, mentioned that all the information about the mission profile, the trajectory, and so on is contained in Appendix A. But I failed to find Appendix A. So I could be wrong, of course. Thanks, Bernard, for having introduced all these subjects, which is quite important. But I recommend to keep an eye on that and to add the Appendix A in the final, at least the version I received. The second question is also a technical one. I am an engineer and I cannot forget that. One of the notoriously most challenging aspect from mechanical engineering point of view, when you approach a small celestial body, small means small mass, means small gravity, means small exchange forces. And if it is high C body and you want to get through, okay, is how you physically do it. Because the moment you push to get through, of course, you risk to be rejected, to rebound, okay? So in the final report is mentioned as a warm-up screw. That could be a possibility. However, talking to my colleagues and friends who are experts on the field, apparently it's very difficult to know whether the ice, in these cases, is hard as a rock, or softy like fresh snow. And the screw, even warm-up screw, may behave very, very differently in the two situations. So at least some assumptions, okay, has to be done. Last and final is a bit outside my field. As I said, I am an engineer, is ethical. Currently, it has been mentioned the Outer Space Treaty and the legal implications, like, among others, the obligation not to contaminate, not to pollute, which is extremely good, but that's legal more than ethical. My question is, you assume to look for biomarker, basically a couple of chemical components, elements. But let's assume for a second, it's really possible to find life, whatever life means, but life is a bit more than a couple of chemical elements. So what would be the ethical obligations, or at least yeah, you understand what I mean, that we as human beings have to respect this maybe possibly real life in our universe.
Okay, thanks for the questions. So initially about the appendix, I believe that might have happened some sort of issue with the versions, but we do approach it in a sense that the MATLAB code used by Mauro regarding the orbital mechanics had around 11 pages, 12 pages of main code, possibly more than 100 pages outside. So we chose not to include that even in the appendix. The appendix only shows pictures of the close-ups of the orbits around each celestial body that was bypassed. Regarding the second question, we would have the orbiter orbiting Enceladus would use the remote sensing instruments to identify the best landing position. Of course, the details of that would come from the LiDAR itself, from the remote sensing instruments, to determine the more suitable position for the landing of so you mentioned for the activation of the screws, for example. And for number three, I would call, please, Ian, could you talk about it?
Oh, hello. Thank you for the question. So I'm as a lawyer, as a space lawyer, and that you said, Professor Maurizio, it's legal in the when you're dealing with OST, international treaties, environmental treaty as well, and the PPP, right? The Police Protection Planet from COSPAR. So, but you ask about the ethics, if it's ethical. So this is quite a hard question, as I can say, because and we don't have an answer for it. You know, we try to and we have a lot of classes about this specific topic, and some workshops about this specific topic about the ethics, but it's hard.
Yeah.
You know, because we have to choose and try to find life in another planet or another place on our solar system or galaxy, and we have this question. It's ethical when you have to get there, or you have to make something, and it's quite hard, and that's why I prefer to stay in PPP policy and COSPAR's policy, because it's what we have now. And of course, the ethical part is still hard to answer.
Ian,
I don't know if it covers everything.
I would like to call Justine. She's very
If
eager
I may
to...
shortly, I would like to really thank you for this very honest reply, which I respect.
Yes, hello, sir. I just wanted to add on top of what Ian said. So the PPP that was written by COSPAR is really focused on the science integrity of the mission. So every requirement that are written in the PPP concerning a lander for Enceladus are really that are just there saying that the probability of inadvertent contamination for Enceladus is 10⁻⁴. So it's not that much. So the science integrity is the main focus of the mission and the legal part of it. One of our suggestions in our paper is for the PPP and the COSPAR and all the legal questions about searching for life is to also take into consideration environmental ethics of the planets. It's not because if there's life or no life that we shouldn't consider the ethic and the environment of the planet.
Thanks, Justine. Yeah, on site we have, I believe, Tayo.
Hello, good afternoon. Thank you very much for this brilliant presentation. So I'm just going to continue with to engage you on topics relating to engineering. So I I think your mission is very nice, but you have to remember that for everything we do in space engineering, we have to understand that space is hard. So it's you have to think about everything that could go wrong. But I mean, in your presentation, there is nothing about risk, about what could go wrong, about how you want to manage this. So I mean, if you have someone in your team who is able to just say one or two sentences about risk analysis for this mission, that would be nice. Also, I want to, if it would be nice if you're able to also talk about the architecture for communication. I mean, it's very nice to have amazing payloads on board, but if you are unable to really send down this data, it makes no sense. So what is the strategy for communication? I mean, you mentioned about using S-band and all of that, but I can imagine that you won't be able to send data point to point from your where you are taking the data to Earth. You need to use some kind of space-based infrastructure and relay satellites. So can you just talk about that? Thank you.
Yes, sure. I'm going to begin with the first question regarding the risks. Also, additionally to risks, right? I would say that the structure we designed was on a very high level, and only as a method to show visually what's envisioned, right? And had we more time, we would definitely insert some finite element analysis as well as a CFD, but that unfortunately was not possible with such a limited structural design. And I'm gonna call Akshata to talk to you about the communications.
Well, thank you so much for the comment about communications architecture. So we have actually included we are going to have relay satellite to the transmission of data via the deep space network. So the orbiter to Earth link will be a radio frequency link, since it is not possible right now to go for a laser link. Also, there are many limitations when we talk about laser. The main idea behind proposing laser as an uplink to the orbiter from the lander is because of the science. Now, we cannot ignore the total communication loss that may occur with laser. So for that, we have X-band, which will still maintain connectivity. Even if laser communications fail to transfer the data, even then we do have the backup system ready to transfer the data. Thank you.
Thanks, Akshata. I do want to bring up a fact that we were limited by 16 pages of text. So it's very hard to choose what comes in and what comes out. Obviously, we have to acknowledge every aspect of space, since it's an interdisciplinary course. And engineering, certainly, although important, definitely we did not have space or time, pun intended, to put as much information regarding risks and the other aspects of engineering. Can we please have Juan next?
Hello, greetings everybody. This is Joan de Dalmau. I'm a graduate of SSP 1989. And my question is in the area of space policy. When I look back at my team project in 1989, where I probably learned most is in space policy, we were proposing a new type of space station to be built in international collaboration. And our faculty were telling us, what you are proposing will not work, because the United States and the Soviet Union will not work together. They will not put their hardware together in space. But we still proposed a roadmap. And your video has very much reminded me of our roadmap, because you started the video with a vision for the year 2100, a vision of a perfect world. So my question to you on space policy and on your possible roadmap towards that ideal world has to do with the BRICS countries. And I suppose that the concept of BRICS countries has been presented to you, perhaps by Professor Peters in his space economics lectures. BRICS stands for Brazil, Russia, India, China, South Africa. 5 countries which are cooperating in space. And as you might have read recently, there is an ongoing initiative among the 5 BRICS countries to do things together in space. So my question is the following. The ISU is going to a very big BRICS country next summer. The first one, Brazil. Have you, in your discussions, in your brainstorming, talked about all those countries that are not in the report? I'm sure you have, because you do say that this will be an international collaboration initiative. But how have you discussed, and what ideas do you have that maybe did not make it to the report about how to get Brazil on board, and Russia and India and China and South Africa? So that's my question, and I congratulate you on the good risk management of your final presentation. You decided to do a recording. That's a good way to manage risk. But it felt sometimes it felt like real life. So really, congratulations for the nice story. Over to you.
Yeah, thanks, Juan. Regarding the communication, the presentation, all the credit, 90% of the credit should go to James and Aruna, who made it happen in such an excellent way. Regarding the BRICS collaboration, certainly we mentioned in the text that the search for life involves international collaboration in every sense of it, since it's something that's directed to humanity, right? And it's something that strives for the curiosity of humankind, right? And to bring up the BRICS certainly is an example that I think should be followed by the rest of the world. The collaboration and the friendship, I would say, that these 5 countries have between themselves is an example by and of itself. And it's funny to mention that, at least in the space sector, we have the BRICS, 2 of those countries which are emerging countries. 2 of those countries are spacefaring nations, now 3 with India, of course. And it's good to see that this is happening. China and India coming at a later stage, Russia being already established in the sector. And then we hope, at least I'm from the Brazilian Space Agency, so that's definitely something that we think about and that we envision for Brazil and South Africa to join that select group. I think the ISU, the SSP next year will be certainly a milestone for us. And we invite everyone to come to Brazil and live in our time zone for a time, because it was crazy to wake up at 4 a.m. every day. But yeah, thanks for your question. Next, can we please have Veronica on site?
Hello. Good afternoon, everyone. So thank you very much for doing this excellent presentation, and also to send over the deliverable, the report, and the executive summary. It's very creative. I mean, there are seminal points. Particularly, I would like to ask you to elaborate on the private funding. So you have been injected a number of novel mechanisms to fund the mission. an hybrid between public expenditure and private investment. Even though there is a two sources that are very innovative for space sector. One, it is the NFT collection. So you end on the blockchain and Bitcoin. This is really the future. Now on board on the station, there are a number of activities to generate NFT from the space asset. So it's really a trend, well done. On the other side, you also identify the lottery. That is an excellent source. I think one of the best example of successful lottery to fund a big endeavor from a financial point of view is the Sydney Opera House. I don't know if you know, but you know, Australian people like a lot to bet. So 92% of the Sydney Opera House has been funded with the lottery. Now, this is an interesting mechanism. I do like because enabling participation of everyone. I just buy a ticket. Simple person on the street, sad, happy, I decide to buy a ticket and bet. I like very much. On the other side, you provide some data that the winning payoff, it is on the order of magnitude of 55%. So, wow. So you are looking for source of funding where you have directly a cost of 55%. So if you get that money, you have already a cost of 55%. How are you going to mitigate this? Thank you.
Thank you for your question. Regarding funding, I would call, please, James, if you can drop it.
Guys, thanks a lot. Great question. There's a lot in there. I guess I'll actually start with the last thing you mentioned. The cost is 55%. How do you think about that? Now, normally in most sort of projects like this, you're probably thinking the cost is up front, but the cost in a lottery is back end. So you buy the tickets, revenue comes in, and then you pay out the cost to the winner. So I think the way you're thinking about that is, how are you going to mitigate the cost factors up front when the revenues come in back end? But it's actually the other way around in a lottery, because the costs themselves are the payout from the lottery, the winners. So from a front end money point of view, it's actually, it's super efficient. But anyway, I know you talked a lot about private funding, but just to start with, I guess I want to talk a little bit about public funding as well, because ultimately, public funding is a political game. Their ability to raise public funding is much more dictated by the public's perception of the thing rather than anything. It's basically a popularity contest. So if you look back in history on NASA's finances, for example, why did NASA get 4.5% of the US national budget in the 60s versus just 50 basis points or so today? I mean, if you think about those in real percentages, I mean, US GDP now is around $21.5 trillion. The US budget's around $6 trillion. So if you're able to get 4.5% of that 6 trillion, you're talking about a budget of around 270 billion versus the 50 billion that it currently is. So why were they able to do that? And the reason why was because they had a theme that galvanized the population in that space race. And for us, we believe the search for life is very similar to that sort of all-encompassing storyline. And we believe expeditions and missions around these sort of things can really, really galvanize the population. And then as a result, that's why we think something like a global lottery could be really powerful, because it gives the average person on the streets the chance to be involved in something that they thought was only for billionaires. But more than that, it gives the individual who's passionate about space the chance to contribute themselves to the things they love and see, their dreams playing out in reality. Now, in your mind, $1 billion is a lot of money, right? But it's actually a very small amount of money if you can get 1 billion people to contribute. And our ideas are trying to bring as many people as physically possible into the space realm, because not only is it amazing having lots and lots of people involved, it also just makes everything miles cheaper.
Thanks, James. Julia would like to give us a quick comment.
Yes, it was just concerning the question of risks that was said some minutes before. I was very intrigued about that question because it was from, I mean, I'm an engineer, an engineer too, and it was one of the first things that I thought in the beginning of the project is that we needed to have redundancy in our systems, because if something goes wrong, we would have another backup. So we were on the decision of having two lenders or just one, or if we would do arbiter or if we do lender, concerning these risks of having a system failing. So we decided for Orbit and Lender because we could get information from both. And if for one case or another we have some failing system in one or another, we still have other systems from the both working that could collect information, and we could still achieve some of our science goals and objectives. So that was my point. Thanks.
Thanks, Julia. I was asked to provide the last question. Since Filomena, sorry, since you've already asked, I'm going to give the opportunity to Hugo, who is on the list. So please.
Hello. Hello, my name is Hugo. Here I am an associated chair in humanitarian department, and in my real life I coordinate the publications and merchandising for ESA. I noticed that your projects, both of them, the presentation, the video, also the executive summary, is extremely interesting and striking how diverse you are there, how many types of graphics, infographics, illustrations, animations you have there. Question, how did you get inspired, and what was your source of, how do you found direction to explain your mission with these graphics and these colors?
Yeah, thanks for the questions. We have our designer here to answer. So please, Priyanka, give us a bit on your imagination.
Hi, thanks. So I have to be honest, the video was all Aruna, and we were all quite excited about how she managed to get all the images. Concerning the executive summary, so we had two deliverables, the executive summary and the full report. And I was kind of inspired by how graphical the previous submissions had been. And I sort of took this up. So I'm actually an engineer with a background, and I'm also a PhD, etc. But I love art and design, and I thought I would take this up as a challenge to try and come up with some infographics. And this was kind of like a fun activity to try and communicate also from the point of view of humanities, that art and design is not something that just happens overnight, and there's a lot of thought process that also goes behind something like this. So it was also kind of like an additional statement, I would say, to this activity for the search of life, that it's not just about science or the business, but it's also this entire art, getting to connect with whoever is reading your report, getting to connect with people, getting them on board on this beautiful expedition for looking for life on other planets. So keeping all of that in mind, I was thinking of designing something that can actually reach out to people in a simple way. Thanks.
Thanks, Priyanka, for your comments. So I would really thank you all for such a excellent course and discussion process. So I give it over to you, Jitu.
Fantastic. Thank you. Thank you very much, Eric. Such an exciting topic indeed, and such a great job you have all done to put this into research and then presentation in such a comprehensive way. So kudos once again. And thank you, Eric, for moderating the Q&A sessions. And thank you very much for all our experts who has been with us for this Q&A session with their questions. So for everyone who are watching online, once again, I would like to say the project report and the executive summary will be on the ISU library webpage, and we highly encourage you to go and read them to get a more comprehensive understanding of the topic that unfortunately the current time is not allowing us to present everything. With that, ladies and gentlemen, this brings us to the end of the final academic deliverable and event of the online Space Studies Program 22 session, which is the team project presentation. So I would like to once again express my sincere congratulations to all our online participants and their supportive chairs and teaching associates for this amazing work, which just happened, I want to emphasize, in only 6 weeks. And I well know how hard you have worked across different time zones for the last 6 weeks to make this possible. I hope that each of you is proud of yourself, which you truly deserve. With that, as the director of SSP22, I hereby declare actually the success of our team project, and it is now time, in a way, to come back home, as we call it, the orbital change. We will sign off for around 2 hours now, and then we will be right back at the SSP22 online session closing ceremony at 5:15 Portuguese time or 6:15 Central European time. So for our audience following us currently online, please follow the same address, isunet.edu/live, when the time comes in around 2 hours, which will take you to a different YouTube link so you can watch the live stream of the closing ceremony of our online program. Thank you once again for joining, and see you shortly.